folks. All right, last lecture video here for chapter 7. Oh wait, that was weak sauce. You thought I forgot about my air horn. I didn't forget about my air horn. Okie dokie, so let's wrap this thing up, folks. So continuing along with Heisenberg Uncertainty Principle. The specific form, the more like famous form, is position and momentum, okay? And what this says is, if position is precisely defined with a large number of superpositions, and remember, the way I can define this with a large number of superpositions is by the following, right? Here, maybe I only have a wave function defined by one superposition, but now as I add more and more and more and more, right, I get more and more precise observation of where the particle is, right? So this delta x here for this particular wave function is very small. Consequently, because Heisenberg says the spread in momentum, or really the uncertainty in momentum times the uncertainty in position, must be greater than or equal to 1/2 h bar, right? As one of these gets smaller, the other has to get bigger, and vice versa, okay? So now, this Heisenberg, as far as momentum and position, that's very specific. As it turns out, Heisenberg is more general, okay? So this is our general Heisenberg term, okay? And so the uncertainty principle is, it applies to any pair of observables that are called complementary. So position and momentum, those are complementary observables, okay? So how do we know if two observables are complementary? Well, they must have this following property, okay? So for example, if we keep working in this position and momentum example, you know, suppose my omega 1 is a position operator and my omega 2 maybe is the momentum operator, right? So these are complementary if, okay? Omega 2 operates on psi first. Then after we carry out that operation, omega 1 operates on the result of omega 2 operating on psi, right? So first omega 2 operates on psi, we get an eigenvalue and the original wave function. Then omega 1 operates on that already carried out operation. So now if we reverse the order of that situation and the two are not equal to each other, then they are complementary, okay? And we say that these two observables do not commute, okay? And the commutator of these observables is now the difference between those two operations, right? So for example, if this left-hand side of the equation equaled this right-hand side of the equation, right? Follow me here. So let's suppose that this was not a does not equal sign, but it were an equal sign, all right? So now if we subtract those two differences, right, and keep in mind, right, look, this side of the equation, this omega 1 operating on the operation of omega 2 operating on psi, right, it's the same thing that I've got here, minus the switch of order, okay? Well, if these two things were identical, then this would just equal 0, okay? And so if those two things were 0, then what would happen here, all right? So what we've got is now this chunk of the general form of Heisenberg. Let me highlight this whole thing. So it's 1/2 times this whole chunk, okay? So this is what we have going on here. It's the absolute value of the root mean square, okay, of the commutator. So that's what this whole chunk is. It's the absolute value of the RMS of the commutator. So if these two observables were to commute, so in other words, if this side of the equation equaled this side of the equation, then if I were to subtract the difference of those two, that would be 0. And so that means omega 1, the uncertainty in omega 1, so that's how this should really go, is this should really be the uncertainty of operator 1 times uncertainty of operator 2. Well, that chunk would would be 0, right? And so what that means is anything times another thing will always be greater than or equal to 0, especially considering if the uncertainty of the operator were 0, right? So in other words, if we had no uncertainty, this just becomes 0 is greater than or equal to 0, which is true. Okay. However, if these do not commute, in other words, if there's a non-zero value between this thing, right? So if we'll say if this does not equal 0, then it is suspect to Heisenberg uncertainty. Okay. So for example, so I think, let me see if I wrote up enough space. So I'll give you an example up here. Okay. So when I write this as bracket x position, comma, momentum, and for now, right, we're just doing things in one dimension. So this means commutator, okay? Just like you can see I have right here, right, there's bracket, observable 1, comma, observable 2, bracket. So that's my commutator. As it turns out for position and momentum, this is equal to I h bar, okay? And so how do I get that? Well, I get that from the following. So I need to go, so I'm going to put it down in this order. So I would say position operates on the operation of momentum on psi, right? So I just said, you know, omega 1, let's call it position, omega 2, let's call it momentum, okay? And I'll just fill this in for you. So the position operator is x. The momentum operator is h bar divided by I d dx, and so that's, right, first derivative of psi of x, okay? So what we would do first is, now, of course, we'd have to know what psi is. We'd have to have a wave function. But we take the first derivative of psi, then we multiply that by h bar over I, then we multiply that result by x. So you can see right away how these two are not going to commute if I change the order of this operation, okay? So now this is going to be, so momentum operator is now h bar over I times d dx. That's my momentum operator, right? And now my position operator is just x times psi of x. And hopefully right away you can see that these two things are not equivalent because there's a chain rule situation going on here. So I'll keep expanding on now this pxx psi x, okay? So the way that this is going to go down now, right, I have to apply the derivative first, or technically I have to say x times psi x, which, boom, there it is, x times psi x. Now I have to take the derivative of that. And when I take the derivative of that, right, there's going to be the chain rule situation, okay? So I'll factor out an h bar over I, because that's just a constant, okay? And so now the first derivative of x is just 1 times psi of x is psi of x, okay? Plus, now remember in the chain rule, I take the x out in front, okay? So that's x. And then now I take the first derivative of psi of x, okay? And so continuing along down here, right, you can see that these two things are not equal to each other. So in other words, here, I'll write this down. So the result of x px psi x, right, was x h bar over I and first derivative of psi. So we can see quite clearly how that does not equal changing the order of operation, h bar over I times the quantity psi x plus x d psi dx, right? And if we wanted to now apply this to the Heisenberg Uncertainty Principle, right, to get this I h bar, then what we would do is subtract these differences, right? So I would take this quantity minus this quantity, and I'm not going to do that. You should try that for yourselves. Hint, hint, wink, wink. And we should get I h bar. And so now if we were to supply I h bar right here, okay, we would then take the absolute value of the root mean square of that. And right, recall when we take I squared, we get -1, okay? Well, first we would take the square root, then we would take the square. But all the same, we would get -1, but because it's the absolute value, we would now just get 1/2 h bar, which is exactly where that 1/2 h bar comes from, okay? And we will apply the general Heisenberg uncertainty equation to a couple of different observables. So linear momentum and position are complementary. As we shall also see later on in the semester, angular momentum and angle become a pair of complementary observables. Okay?